Welcome to Math 2318, Section 1.9. In this section, we have an interesting topic, and that is we have a linear transformation, T, and we want to find the matrix that is associated with this transformation. Well, first off, if my transformation is from R2 to R4, the size of this matrix starts at the range, and so it's 4 by 2. This matrix is determined exclusively by what T does to E1, E2, E3, E4, your basis vectors. And we'll see what that word basis means at a later date. But for now, the matrix A is completely determined by what T does to these vectors. So in our case, T of 1, 0 goes to 5, 1, 5, 1, which is the first column in matrix A. T of 0, 1 goes to minus 3, 4, 0, 0, and so that is the second column in matrix A. So again, to do the transformation, I could use the formula for T, or I could use it as a matrix multiplication of A times X. All right, what's going on here? Let's see. First off, T is a transformation going from R3 to R2. It's defined, T of X is A times X. A is 2 by 3. 2 rows, 3 columns. And again, it's completely determined by what it does to E1, E2, and E3. So let's see. T of E1 is 1, 7, and that's the first column. T of E2 is minus 5, 8. T of E3 is 7 and minus 2. All right, let's see. In question 3, we have a transformation. We want to look at what's called the rotation matrix. This is from R2 to R2, so my matrix is 2 by 2. So let's talk a little bit about this rotation. So the question is, what does it do to my basis vectors? So T of I and J for R2, which is E1, and so basically I'm looking at T of 1, 0, and I'm looking at T of 0, 1. So let's look at this picture here. So here's 1, 0. It gets rotated through an angle theta. And if you think of this as the standard unit circle, then if this is theta, then the lengths of these two sides are cosine theta, sine theta. So where did 1, 0 go to? It gets moved to cosine theta, sine theta. Well, what about J? J points up the y-axis here. At 0, 1, it gets moved through an angle theta. And so if you look at how that applies to its coordinates, it's minus sine theta, cosine theta. So our rotation matrix through a counterclockwise rotation in the plane is given by matrix A there. And so in our case, we're looking at A of 5 pi over 4. So I simply plug that into the sines and the cosines. Where is 5 pi over 4? 5 pi over 4 is past 180 or pi, which is 4 pi over 4, and it's pi over 4 farther, and that's the reference angle. So, in terms of the reference angle, we need the signs, plus and minus for sine, cosine, and tangent in the different quadrants. And in quadrant 3, which is where 5 pi over 4 is, sine and cosine are both negative. If you look at the standard 45-degree triangle, the lengths of the sides are 1, 1, and square root 2. So cosine of 5 pi over 4 is 1 over square root 2. It's in the third quadrant, and so it's negative. And so when you fill all of that in, you get what the rotation matrix looks like in the plane for an angle of 5 pi over 2. Alright, in this case, we're rotating through minus pi over 2. Same rotation matrix. I'm looking at minus pi over 2. Well, where is minus pi over 2? Minus pi over 2 is the same as in a positive direction, 3, or a counterclockwise direction normally, as 3 pi over 2. And so calculating those values, we get our rotation matrix through minus pi over 2. Alright, so let's see. We'd like to figure out what is the matrix that goes with this transformation. So what does it do? They say it's a vertical shear that maps E1 into this matrix, or this vector, sorry. So T of E1 is T of 1, 0, goes into E1 minus 6E2. What does that look like? Well, that's 1, 0 minus 0, 6, which is 1 minus 6. And that's the first column in matrix A. And it says we leave E2 unchanged. So T of E2 is E2, which is 0, 1. So here's our matrix that does this particular transformation. All right, in question 6 here, we're looking at two things. First off, we are reflecting through the vertical x-axis, and then we're going to reflect through the origin. So let's see, what does that mean if we're going to reflect vertically? So here's the x2 axis. I'm reflecting. So when I do this reflection, E1 comes this way, which is the negative of it. If I'm simply reflecting about the x2 axis, nothing happens to that. And so my matrix, just for that, the vertical reflection, would look like matrix A. Now I can think of this as the composition of two transformations. First one does the reflection, and then the second transformation reflects about the origin. Alright, so let's look at this origin reflection. So the origin reflection is E1 goes to minus E1. E2 reflects as well to minus E2. And so here's my matrix that does the reflection about the origin. So if you think about what's going on here, what we have is this matrix does my reflection about x2. It operates on this particular vector, and then the reflection about the origin takes place. Well, this combination, whether it's a composition of transformation, turns out to be, with our matrices, a multiplication. And so this is my matrix here that does this composition of the two actions. All right, looking at question 17, or in the book 17, question 7 here. So here they're giving me a formula. T of x1, x2, x3, x4 has an image which is found in this way, dependent upon x1, x2, x3. So we want to find the matrix that goes with this. Well, don't overthink this. Just use the formula. What does T do to E1, E2, E3, and E4? I mean, you simply plug it in. And so T of E1 looks like this. T of E2 goes to this. T of E3 goes to all zeros. And T of E4 looks like that. And so we simply have our matrix A, which is what T does to each of E1, E2, E3, and E4. All right, in this question, question 8, I want to find an x1 and an x2 where it gets mapped into 1 and 14. So we have a situation here. We have a transformation T. I'm trying to figure out what particular vector gets mapped under the transformation into 1 and 14. So I simply need x1 plus x2 to be 1 and 4x2 plus 4x1 plus 2x2 to be 14. And so I simply solve this system of equations, and I find out that the vector that goes there looks like 6 minus 5.